Chapter 6, Part 2. Let's get started. So, we want to know what caused the orderly pattern of motion in our solar system. And I will later on in a little bit, I'll show you this in an extra file. But let's move on, and I'll show all of these to you shortly, okay, in a little bit. We also had in our solar system conservation of angular momentum. So what it means really is this, that all of these particles, okay, all of these particles that are around in different distance from the central star, they're all getting condensed, right? They're all getting closer and closer to the central uh, point, which is exactly where the star is. As they are moving from a further point to a closer point, in other words, they're losing their distance, okay? So remember L, which was the angular momentum, was R cross P. Distance cross regular momentum is angular momentum. So if the angular momentum, which is L, is conserved, it does not change, which is the case for our solar system, right? If this guy is conserved, if R is getting smaller and smaller and smaller, in order to have this value a constant value, P should go up. Okay, so what was P? P was regular momentum, if you remember, which was mass times velocity, right? So if I want P to go up, the convenient way of increasing the P is to increase the velocity of it, right? So that's why the disk, as it was shrinking, it started to move. And so it started to move actually pretty fast. And now I will show you another animation about it in a little bit, okay? Which is right here. So you can see the rotation. As these materials are collapsing, they're starting to rotating faster and faster. So eventually, because of collision between these particles in a solar nebula, because they're all colliding together, they started to also flatten to a disk. So you had a wider materials that are still rotating, but because of collision between these particles, it started to flatten to a very, very thin disk now, right? And eventually all of these particles, if they are moving in a random directions, they started to going in the same direction. So two particles are moving with different velocities, different portions in the disk. They collided with one another and they started to move in the same direction, pretty close to one another. So that's why the disk gets flattened and also gets thinner at the same time. So again, I'll show all of these to you in a little bit. We also have found the same stuff happening in the other solar system outside of our own planetary system, right? So we have seen it in the observations, especially with ALMA telescope, have shown us the nebular hypothesis is actually correct. So you can kind of see that there's also gaps in the disk. So these are not in our own solar system. This is somewhere else where you have the central star, but there are gaps here. Do you see these gaps? These gaps because there is another planet is forming here, probably a hot Jupiter or a planet like Jupiter. So do you see these gaps? It's because there's a planet there, it's forming, and it's just eating all of the gases and dust that's around it. So that's why there are these gaps here. So we have seen the same stuff happening in other solar systems. Now, there are two, if you remember from previous chapter or previous part, there are two major planets in our solar system: the terrestrial planets, which are rocky stuff, and Jovian planets, which are gaseous and iceous stuff. Okay, so the reason for that is pretty easy to explain because the terrestrial planets form in a region which was so hot, so all of the ices that were there couldn't condense. And Jovian planets form in a position in a solar nebula which was so cold that these ices could condense on the surface of these dusty grains. So that's why they are dusty, or that's why they are icy, in fact. And so that's the reason. But there are uh, the major elements in our solar nebula is hydrogen and helium, which made up almost up to 98%, and they don't condense anywhere. So they're just there, even if it's really cold or if it's really hot, it doesn't matter. They don't condense. Hydrogen and helium are just gas. And then you have hydrogen compounds. Hydrogen compounds means you have hydrogen, but that hydrogen is have a bound with another atom in a form of a molecule. So you have water, methane, ethane, ammonia, formaldehyde, and so on. And they're usually condensed in a cold temperature less than 150 Kelvin. And then you have rocks, which are these dusty materials, right? In order for them to condense, you have to have a temperature of 500 to 1300. So they made up about 0.4%, so less than 1%. And you have metals, which is iron, nickel, aluminum, things like that. And they made up to 0.2% of the material. So most of the solar nebula is hydrogen and helium for sure. And so as you're getting closer to the central star, you are in fact closer to the higher temperature, so higher temperature. Okay, so that's why we have a frost line. The frost line here means that if you are closer to the frost line, the temperature is high enough that these materials cannot condense. So you don't see you don't see an icy or icy material inside. So that's where the terrestrial planets form. Okay, out in the outer part of a solar system, beyond the frost line, and sometimes we call this a snow line as well. That's why the material can condense and form ice on the surface of dust grains. So that's why we have juvenile planets forming there. So smaller particles of rock and metal were present inside the frost line. I was just talking about it. And the planetesimals of rock and metal build up of these particles that collided. So gravity eventually assembled these planetesimals into terrestrial planets. Now, I will show you how the accretion is happening. So accretion, remember, the accretion is a very simple process, in fact. You have these small particles, small grains that are colliding. They stick together, they build up to pebbles, to rocks and boulders, and so on. So it's getting bigger and bigger. The same is true for ice. If you're outside of a frost line, the same would happen to you. So, the accretion will again happen. And so this is what the accretion really means. We have a central star and you have a bunch of these particles that are rotating around, tiny particles, big particles, but they eventually collide and they stick together due to very small gravity over millions of years. Then what you have is a planet that is going to clean up its entire orbit. So anything that's in the orbit of the planet will be part of a planet eventually, except if they are in a resonance with the planet. For example, Jupiter, let's call this one Jupiter, okay? There are a lot of these little particles, little, asteroid type particles that are called Trojan. They are in two different locations with respect to Jupiter, okay? So this is Jupiter, this is Trojan group number 1, this is Trojan group number 2, and they are in a resonance with Jupiter, meaning that they all are moving with the same velocity as the Jupiter. So they can't, because they're living in a resonance with Jupiter, they cannot go and be part of the Jupiter. So they're tiny particles, not tiny particles in fact, some of them are tiny, but there are these groups of particles and objects that are having the same orbital period as Jupiter. But other than that, a planet will eventually clean up its own everything around it. And we've seen it in the other planetary, in other solar systems before. So now, Formation of the Juvian planets, as I was just talking about, it's pretty similar. So ice could also form small particles outside of frost line. So larger planetesimals in planet were able to form, and that's true. The gravity of these large planets were able to draw the surrounding hydrogen and helium. Remember, the hydrogen and helium were about 98% of everything that we had in solar nebula. So they were pretty abundant. There were so many of these particles. And the formation of the Jovian planets also pretty similar. You have an ice. So these ices are condensed on the surface of dust grains, and they eventually pull in surrounding material. And so they eventually form a Jovian planet. You've seen it in this picture. So you have the central star here, but you have seen that there's a hot Jupiter here. And then you can see that there's a disk around Jupiter itself will probably cause a lot of these particles to form moon around the Jupiter. And we have seen it in other solar system. And then once the solar wind starts, in the solar wind, all these highly charged particles that are going insane, they start from the central star and they move out with a high velocity. And that's one of the reasons that Mars doesn't have that thick of the atmosphere right now, is because the solar wind blown away its atmosphere. Solar wind cannot blow away our atmosphere because we have a electromagnetic shielding protection, right? But solar wind is just these highly charged particles that caused the leftover of hydrogen and helium to be completely blown away from our solar system. So that's why there are so many gaps between the planets now, right? So let me go ahead and share another page with you. So here we go. So this is what I was talking about. So planets are in different forms. So let's start with our sun. The axis tilt is about 7.25 degrees, and a rotation period is about 25 Earth days. So sun will, it rotates around itself every 25 days or so. And this is something that you will do in chapter 11. You will go and do an observation, and you will eventually end up to find the 25 Earth day rotation period for the sun. Next, we have Mercury. Doesn't have any axis tilt. The length of day in Mercury is 58 days, and it's the first and closest planet to the central star. We have Venus, and Venus has this axis tilt, which is 177, but it really depends on how you're looking at it. So you can look at it and say that this is not really the axis tilt, and the axis tilt is in this direction. But I think the way that we're talking about it here means that we are considering the North Pole and South Pole. So that's why we're talking it's 177. Depends on which direction you're talking about. But it still has a little bit of an axis tilt compared to, this dotted line, if you're looking at it in this direction. Next, we have Earth, 23.45 degrees, and the length of a day is just 1 day. We have Mars, pretty similar axis tilt. However, the eccentricity for its orbit, it's a little bit more compared to Earth. And the length of a day is pretty similar, 1.0226 Earth day. Jupiter, 3 degrees axis tilt. It rotates way faster, so that's why it's also not 100% spherical, because it's rotating very fast. So the length of a day is about 0.4 of the Earth day. So that means the Jupiter with that massive size is actually moving pretty fast. The same is true for Saturn, 0.44, which is the length of a day. But the axis tilt is way more than Jupiter, which is about 26 degrees. Uranus, 97 degrees. We don't really know why. We think that it's because of a massive collision that it had with another planet before. But it is still rotating faster than Earth, 72, so it's less than 1 day on Earth. Neptune, 0.67 Earth day, and the axis tilt is 29 degrees. And Pluto, dwarf planet Pluto, the axis tilt is weird. The length for the day is 6.39. So it'll take 1 week on Earth almost for the Pluto to do one full rotation. And it's very tilted with respect to the solar system. It's weird. And so it is well inside a Kuiper belt, but in a tilted way. So that's why it has a comet-like composition. All right, let me come over here and play this for you. This is what I was talking about, where you have these gases collapsing. And so as they're collapsing, the temperature is getting hotter in the center. And so they're starting to gaining angular momentum and starting to rotating faster and faster. Due to collision, they start to flatten. And so you will eventually have a very thin disk with a central hottest star at the center. So you can see them in two different views, actually. So you can kind of see what I'm talking about when I say that the disk will get flat and flat and flat. This is what I'm talking about. So the edge-on view is telling you that how flat and thin the disk is, where the central star is a little bit thicker, but as you're moving away to the other side, and this is exactly what we call this the ecliptic plane. Now let's talk about why it's getting flattened, because of a collision of these two particles, or any particle. Particles are colliding, right? So as they're colliding, they're starting to, so they were so way, distant from one another, but then once they collided, they're starting to move together. And this is exactly what happened to most of these particles in a protosolar nebula. So I think I played this before, so let's go to this. So here, you're inside the frost line, right? So that's why there aren't many particles inside. So let's take a look. So these particles are getting closer and closer together. They stick together, so they build up to more massive particles eventually, right? And if you go outside and you do the same, you see that the same is true, but this time you have ice that are sticking to the dust grains. So that's why whatever the material that's being produced out there, they're more icy. And so this is the formation of the Jovian planets. They are accumulating more and more, so they're getting massive and massive and massive. Same for the terrestrial planets, but in the case of Jovian planets, you can see that they are more icy and gaseous compared to rocky planets inside. And so eventually solar wind, once the solar wind starts, it wipes out everything that was in between these planets. So all the remaining leftover gas and dust will eventually blown away by the solar wind. So that's why between these planets, we have so many empty spaces, right? All right, end of part 2 of chapter 6. We'll go to part 3 right after this one, okay? Stay tuned.